In particular, we discussed compactification at r is equal to square root alpha prime. This is the self-dual radius because an r prime is equal to alpha prime by r is also equal to r at this point. We discussed the toroidal compactification. We discussed the toroidal compactification of this radius has a worldsheet theory with an underlying SU2 times SU2 Cauchy-Moody algebra. The generators of that Cauchy-Moody algebra were J3 is equal to I. What was it? I. Somebody remember it? Del x. Del x e to the power I.
Plus minus 2i x by root
square root alpha y square root alpha prime.
J plus minus, and here there was
1 over root alpha.
1 by root alpha prime.
1 by root alpha prime, and there was a similar thing on the right. And we discussed that this was related to TUL. And perhaps you remember the relationship. One way of saying the relationship was that increasing the size of a circle is adding this operator, the worldsheet theory. Increasing from a fractional increase. Okay, so adding this operator with a plus epsilon or a minus epsilon gives you the same fractional increase or decrease in the radius from the self-dual point. Okay, so T-duality about the self-dual point for infinitesimal translations is the statement that an infinitesimal increase in the radius is the same as an infinitesimal decrease in the radius. Right? Because 1 minus epsilon should be the same as 1 plus epsilon. Okay, but we argued that this was just the case coming from this SU2 times SU2 symmetry. Because, for instance, you could perform an SU2 transformation on the left, which rotated. So this was just J3 times J3. And you can perform an SU2 transformation on the left, but none on the right. So leave J3 tilde unchanged. And the one on the left could be, for instance, a 180-degree rotation around the x-axis, which will flip Jz to minus Jz. So it will turn this around. Okay? So the symmetry of the theory which relates these two. Okay? Moreover, we discussed that this symmetry, which is an exact symmetry of the worldsheet of the string, turns into a gauge invariance in space-time. And so, this symmetry, so even though we don't know what non-perturbative string theory is, assuming it makes sense, the symmetry had better be a non-perturbative gauge symmetry of the whole theory. Right? So this helped us identify the nature of T-duality. It's a gauge invariance from the space-time theory. It must be exact, assuming it is exact. Okay? Very good. Now, there are various other things that we... at the end of the last class, we had discussed the massless manifold of objects. Here, you remember we had these 9 different scalars. Okay, and we have these 9 different scalars, which was Ji, J tilde J, whose vertex operators were Ji and J tilde J. We call these scalars Galas MIJ. And we discussed that there was at the 3-point function level, at the cubic level, a potential for these scalars in space-time of the form basically T. Right? Just epsilon I j k, epsilon I tilde j tilde k tilde, m I tilde, m j tilde, m k tilde. Do you remember where this came from? This came from just a vertex operator calculation. So the 3-point function of 3 j's had an epsilon I j k. We saw that from the OPE of the j's. Yeah. Because j went with j with the structure constant, which is epsilon. Okay, the 3-point function of 3 j tilde at this. So the 3-point function of the product of these two. So that's essentially the calculation. Okay? And in the last class I asked you to check what the flat directions of this potential. Are you going to try this? Okay, fine. So, the potential is the determinant of M. So what are the equations of motion? You vary the determinant of M. When you vary the determinant of M, what do you get? So let's suppose we've got a 3x3 determinant, and I vary with respect to the ijth element. Okay? What I get is the minor of the ijth element. The determinant of the 2x2 matrix obtained by omitting the ith row and the jth column. Because that's what the determinant is. It's the ijth element times its minor summed over all elements. So, the only kind of matrices that obey the equations of motion are those for which every 2x2 minor, the determinant of every 2x2 submatrix in the big matrix, vanishes. But you don't name for matrices that have this property. That you form any 2x2 matrix, you've got 3-dimensional matrix. You form any 2x2 matrix in this big matrix, and its determinant vanishes. These are matrices of rank 1. Because the rank is the largest submatrix. Yeah. Okay? Whose determinant is non-vanishing? So forget 3x3. I mean, clearly the full determinant vanishes, all the minors vanish. But every 2x2 determinant also vanishes inside this matrix. Which means that the rank of this matrix is 1, maybe 0. Okay, if the rank of the matrix is 0, then every element in M was 0, so that's a solution. M equals 0 is a solution, fine. But there are more solutions. Every matrix of rank 1 is a solution to these equations. But the thing about matrices of rank 1 is that any matrix of rank 1 is a vector times itself. MIJ because you see, what is a matrix of rank 1? A matrix of rank 1 is basically something which is just in the right basis, it's just this element, and everything else is in it. Suppose, see, every matrix can be written as a linear combination of things of this form. Suppose there were two guys and they were not linearly equivalent, you easily see that as a rank 2. If you don't know this, you can easily convince yourself of this. So every matrix is something of this form. But now we have SU2 times SU2. So we can SU2 left acts on this, SU2 right acts on that. So you can independently use SU2 times SU2 to put each of these two C's in the Z direction. Okay? So the most general solution up to SU2 times SU2 of the equation of motion is M33. M33 is equal to alpha. Everything else is equal to 0. So the most general flat direction is this one. Adding J3 tilde with an arbitrary coefficient up to SU2 times SU2. Now we've only checked that this is a flat direction at cubic order. But we know independently that this defines an exact conformity. This determination defines an exact conformity. And so, the fact that this is a flat direction must be true to all orders in, as an exact statement. So, quartic higher order corrections can't change that. The fact that all others are not a flat direction cannot be changed by higher order corrections. Go on.
We lost it.
Yes, please.
Just one line summary.
The summary is a first. We've got a potential for this M field. We've got these 9 M fields, and we want to understand the structure of the potential in space. Okay? M equals 0 is a 0 of this potential. I want to know Yeah, I want to know what is the full manifold of V equals 0 potentials. Okay? You see, V equals 0, well, what I want to know is the full manifold of solutions to the equations of motion that come from this potential. But that can only be a flat direction. Because if you've got some potential like this, then the equations of motion won't be satisfied, they'll push it out to 0. Okay? So, the solutions to the equations of motion are all the objects with the lowest possible, with the same potential as any one solution.
Basically, we are computing the extremas of the potential.
Extrema of the potential, but they will also have the equal potential because the variation of the potential along this branch is 0. So if you've got a one parameter set, they all have the same potential. That's right. We're extremizing this potential. We know one of the extremas m equals 0. That is v equals 0. Okay? So I'm computing the flat direction. So the extremal points which also will automatically have v equals 0. Is this clear? Okay? Now, okay, what we did was we solved the equations of motion. We found all extremal points. We found that the extremal points, the solutions to the equations of motion, were all matrices of rank 1. Up to SU2 times SU2, we could turn all matrices rank 1 to matrices with only trinitary components, non-zero. Okay, so up to SU2 times SU2 transformations, we found that this potential had a single flat direction. Remember, directions that were equivalent by SU2 times SU2 were not to be considered different, because that was a gating variance. Okay? So there is essentially a single flat direction. Okay? Now what was the flat direction? The flat direction was taking the original theory and deforming it by J3 J3. Now, I've only done the infinitesimal calculation around the point m equals 0, because I've only computed the cubic. I've not computed a quartic order, 5th order, 6th order. In general, the 20th order guy may turn out to lift this exact flat direction. Okay? So, cubic calculation cannot establish that you've got an exact flat direction. However, it can establish that you don't have a flat direction. We know that every other deformation of n, apart from those that we've listed here, apart from these rank 1 deformations, are not flat. Because you see, if the equation of motion is not obeyed because of the cubic potential, a quartic correction to the action cannot fix that up. Because at infinitesimal values of n, the cubic guy always dominates over the quartic. Okay? So what this calculation is sufficient to do is to establish that there are no other exactly flat directions. Exact conformity. And mixing up various ways of speaking, which are mixing up space-time and world sheet. And this is done partly because I'm being lazy, but the advantage of my laziness is that you should get used to it. Okay? Because, you see, solutions to equations of motion in space-time, these are flat directions, space-time potential, are conformal field theories on the world sheet. Okay? So every solution to the equation of motion in space-time is a conformal field. So, the question of whether there exists a flat direction, exactly flat direction in space-time, is this at the classical level of space-time. It's exactly the same question. It's whether there exists a one-parameter set of conformal field theories. Okay? So, if this flat direction really exists, we should be able to identify the one-parameter set of conformal field theories. But we can, because this conformal field theory, this definition just changes the radius of compactification of the world sheet theory. Now, I want to make sure everyone understands that last thing. Can somebody explain to me why adding this changes the radius of compactification of the world sheet? Hey people, if you're not understanding something I'm saying or you're only half understanding it, you should stop.
It's like taking G25.
It's like taking excellent. That's an excellent way to say it. G25, but I'll say it in 2 or 3 different ways just so that excellent. Which is just so that it's clear. So what? Suppose we had the conformal field theory with R25 equal to R25. I'm just calling it R, okay? Expression. I'm going to call it X. X is equal to X plus 2 pi R. Okay? And we're working with the action S is equal to 1 by 4 pi alpha prime. Del alpha X, del alpha X. Now, to this action I add a plus epsilon plus finite plus zeta times that J3, which is again del alpha X, because J3 was del X, J3 bar was del bar X, and del X, del bar X is del alpha X. Up to some 2 or something like that. So this is the action. Now I can change this to, I'll redefine y is equal to 1 over square root of 1 plus zeta times x. Okay? So this action, because S is equal to 1 plus zeta over 4 pi alpha prime del alpha x is clearly 1 is just 1 by 4 pi alpha prime del alpha y. So I've gone back to the same action as without the deformation, but with one change, that the periodicity of y is not the same as the periodicity of x. They differ by its factor of 1 plus square root of zeta. So you see that adding this term to the action just corresponds to rescaling the periodic identification of x. Okay? Another way of saying it is what Yogesh said. Yogesh said is that adding this is just like changing G25 to just by putting a constant G25 here. And then from the point of view of space-time, it is totally obvious that changing G25 to a constant can be undone by a space-time diffeomorphism, coordinate change, but that will then rescale the identification. In fact, these two arguments are the same thing. Because you see, a space-time diffeomorphism is what? It's a change of moving to one coordinate which is function of another coordinate. How does string theory see space-time diffeomorphism in that? Field redefinitions, exactly, because space-time coordinates in space-time are fields on the world sheet. So, and the fact that the Lagrangian doesn't care, it just cares about your sigma model, not about the variable. The path that doesn't care about what variables you use. You do field redefinition. That's what we done. We did a field redefinition in our Lagrangian. The way Yogesh would have said it is that we do a coordinate change in space-time. But that's exactly the same.
J plus minus should also do the same thing, because you can use SC2 to rotate the term.
J plus minus also does the same thing. Excellent. So, Rohan's made an excellent point. One point is the following. Look, suppose I take del x bar, or del bar x, plus alpha times j plus e bar I. Let's say e to the power 2I xl plus times e to the power 2, either plus or minus, it doesn't matter, 2I xr. We have independent rotations. Okay. Suppose I have this action here. Okay? Where this is self-duly identified. Then this can be written as plus alpha e to the power I 2I x. Because x is xn plus xn. Okay? So Rohan's point is that look, you start with this action. More precisely, I should have done something real. Because you see, J3 cannot be rotated to J plus.
Oh yeah, J plus I plus I.
It could be rotated to J1 or J2. You do this carefully, you will basically get this plus complex.
Yeah, and then
Okay, this is a real action now. Whole thing makes sense. You have to do that a bit carefully. But you will essentially conclude that this action is actually a free action. Okay? And this is an amazing statement because this looks like a very complicated action. Okay? In fact, this action has a name. It's called sine Gordon theory. Okay? Because you've got a free boson deformed by sine, cosine, all those activities. Potential. Okay? But the fact that the sine Gordon, the massless sine Gordon theory, the thing without mass, without a m squared term, is actually a free theory, is a famous fact discovered in the 1970s. It's part of the statement of what's called sine Gordon theory. Okay? The way people said it there was that it was dual to a free fermion, but a free fermion and a periodic scalar at self-dual radius are actually the same thing because of bosonization. We're going to study all this. All this. So this is an example of a field theory that, by Rohan's proof, despite looking extremely complicated, look at the potential. It's got some sign potential. It's actually a free theory.
How do you see it?
We see this because this is equivalent to a J3 J3 multiplication by SU2 times SU2, which is a free theory. It's just rescaling the bosons. Okay? So, this, what you said, Rohan, is true. And it illustrates how powerful this SU2 times SU2 is. If you just written down this theory, A, it would have been far from clear that it was an exact conformal field. B, it would have been far from clear that it was solved. Both statements are true. This guy looks like it has a terrible potential. No potential. Yeah, it's all. Yeah, this is the beginning of a rich story involving various interesting duality. Okay, but we will not. At this point, we will not touch it. Okay, excellent question. Any other questions?
Choosing one point along this flat direction is choosing a particular CFT based on the...
Yes, or equivalent to a particular certain size. Okay, so once we've identified what the CFT is, we realize we've learned nothing new. Because we always knew that there were conformal field theories with periodic identification at every size. All that this has shown us is that there's another, you can approach these conformal field theories by particular definitions from this self-dual point. We haven't learned anything new. What would be more interesting is if there was another direction out from the self-dual point. Another class of conformal field theories which had no geometrical analog, couldn't reach from circle compactification. But unfortunately that's not true.
Sorry,
Yes.
Can you please remind me why J3 tilde prime, J3 tilde potential is same as J plus J minus potential?
Same as J1, J1. Because J3 can be rotated by SU2 left to J1.
I see.
And J3 tilde can be rotated by SU2 right. Okay, clear?
in short, T duality should give you dualities between different conformal field theories that you can obtain from different points on it.
Yeah, so T duality tells you that this line, which looked like it went from 0 to infinity, actually only goes from square root alpha prime to infinity. Because point here is J equivalent to point here. Halves the space of things. That's something you want to ask of me?
Thinking that if you expand x in Fourier basis, This looks like a shift. If you think of it, this actually the basis vector E to G.
Yeah. It looks like something. It looks like you're saying you're exponentiating it looks like you're adding a mode of a particular momentum. Yeah. Exactly. Which is a sign. It looks like you're adding this from the point of view of space. Okay, no, from the point of view of the world sheet, it's adding a potential like this with a particular frequency. So it looks totally different time to 3. Looks like things will be localized here. I mean, it looks totally different, but it's the same.
This potential is mass term everywhere, right? You said massless.
What?
You said the massless. You said something about massless.
Massless meaning you don't add a plus in squared. You don't explicitly add it.
But such a time is always added to you.
There is this term, but there's no further, nothing other than this. Sorry, that's right. Okay. I say this because there is a well-known integrable deformation on this theory, which is what people really call the cycle. It's a massive theory. That theory has this is confirmed theory. It's famous that theory. Okay, but there's a well-known integrable deformation that basically that is mass term, which is also an exactly solvable theory. S matrix has been computed exactly. So there's this little window into a very rich mixer. Try to get it. Okay. Yes. Sure. Vishal, you have a question?
Suppose you are given some random potential, free part and some random potential.
Yes.
Actually, in principle, know if this is obtained by from a free theory, tell me x prime, and just x prime goes to f of x.
If you do that, then you will also get a funny kinetic terms.
But suppose in the power series, some infinite power series x prime, then you choose the coefficients as the kinetic term. Like you arrange for its cancellation.
I don't think you can do that. Let's try it. Suppose I do x is a function of y. Let's call that function whatever it is f. Okay? So the kinetic term will become what? Will become some g of y. Okay? Will become some g of y del y del power y. What was this g? Okay, this g was del x by del y above x square. Okay, if you want the kinetic term remain unchanged, del x by del y is all stretched to 1, which means del x by del y is 1, which means x is equal to y. So I don't think you can do that.
But what this exercise says that if you want to see something of kinetic plus potential as a free theory, you just need to redefine your field such that it arranges itself
It becomes a more
only as a kinetic.
general question that given a free field theory, if I do some very complicated field
redefinition,
finally see that it's still a free theory.
How do you finally see that as a free theory? Exactly. You can, first is doing this field redefinition will give you just this. It will not even give you a potential. Because every term will have some derivative. There's no term without a derivative. Okay? That's basically, in the space of fields, that's the question of the metric. Here, with just a free theory, every such thing can be brought to this form by an appropriate field. Yes. Okay? But suppose there was a yi, yj, then you have a gij. Then when can you bring this to the free form? When the metric gij is? More than that?
It's diagonal.
More than that?
Unique diagonals.
Has zero curvatures. Because you're trying to do a variable change. Your field definition is a space-time coordinate change. You're doing a variable change between gij to ij. It has to have zero curvature. So, in general, this metric can be brought to the free form if in the metric in field space it's flat, or not otherwise. Okay, so Ashish's question, which seems like a complicated mathematical question, it was a complicated mathematical question. Luckily, it's been answered. Not by field theorists, but by geometrists. If we didn't know about geometry, we would have a hard time answering this question. Okay. Other questions or comments?
So last time we were discussing this mixing from SU2 cross SU2 to
Yes.
SU2 cross U1.
Yes.
So we had to study the Goldstone.
You understand that a little bit. Let's try that. Okay. I work out only the Higgs pattern that actually exists, which means by turning on J3. Okay. So, what did you start with? You started with SU2 times SU2. How many massless gauge bosons? In space time? 9? 6?
3.
It's 3 plus 3, not 3 times. Yeah. Okay. So, 6 massless gauge bosons. Okay. Now at a generic radius, how many massless gauge bosons are there?
I mean, we just have one flat direction.
No, the flat direction and massless gauge bosons are different questions. At any one point along this flat direction, how many? There is a question for a conformal field theory compactified at a given circle radius. How many massless gauge bosons? It's the same everywhere, so you can do it in geometry. Or you can do it. Okay, I'd like you to answer both by vertex operators as well as by geometry. Hey, come on, people. I'm getting a bit scared that this class is becoming into a spectator sport. Explain to me why from vertex operators why there were 6 massless gauge bosons. What were the vertex operators for the gauge bosons?
Ji, J tilde.
Those were massless scalars, not massless gauge bosons. Those indeed were 9.
You need space-time in this case. So
Good.
J plus into the remaining.
Excellent. So it was J left times del bar x I.
Nice. Yeah.
Or J right times del x. Right, because this is left moving, so you need, this is 1 0, so you need to add a 0 1. This is 0 1, so you need to add a 0 1 0. These were the 6 gauge bosons. 3 here, 3 here. Okay. Away from the self-dual radius, which of these JL, JRs, let's stick to JLs, which of the J's continue to be 1 0?
Oh, the J3 ones.
J3. Because you have to change, e to the power 2I XL by square root alpha prime always is dimension 1. But it's not a well-defined operator. Unless x has the right periodicity. So you have to change this coefficient to make it a well-defined operator. Is this clear? Is this clear? Okay? So these guys will no longer be J plus and J minus will no longer be 1 0 operators. So you continue to have a vertex operator like this. But it will not be a massless, it will not corresponding to massless. I mean, you will continue to have some kind of vertex operator, but you would have to match with something else on the right. Okay, lots of things you have to do. Okay? There is no massless particle, no massless gauge boson. Okay, there's no massless gauge boson. Okay, away from the self-tube. Is this clear? Okay. Now, how many would remain? So, how many gauge bosons would remain away from the self-tube? J plus and J minus don't correspond. What does?
So J3 and J3 plus.
So, what remains is 2.
Yeah, 2.
Be away from the center. Okay? So, what's happening is that we had 6 massless gauge bosons, and now it's becoming 2. Okay? First, next question, how do you see these 2 massless gauge bosons from geometry? Gravity theory, you compactify it on a circle. I'm claiming there are 2 massless gauge bosons. Where? What?
Oh, so they will be the Kaluza-Klein.
Kaluza-Klein?
I mean that part of the metric which is not.
Good. So G25I
yeah.
is one of the massless gauge bosons. Wherever the other.
So other one should be the. One should correspond to the winding.
Excellent.
Yeah.
As a hint, I'm going to work out the vertex operators. So we have del x25, that was J left, times del bar xi, or we have del bar x25, del x times.
Yeah.
Now, what was your G25i? What is the vertex operator for that?
So linear combinations of these.
Which linear?
This del x25
plus
del bar,
because
yeah.
G is symmetric.
Yeah.
So what's the second linear combination?
So this is
with
negative,
minus.
yeah, minus.
This is the vertex operator for what? For the gauge field, but in general in string theory, you have a polarization zeta mu mu del x mu del bar x mu. If this polarization vector is antisymmetric, what particle space length is that? V mu nu.
Oh, wait.
Okay, so V mu nu is a 2-index object. You take one of its indices to be 25.
Oh, wait.
It gives you a gauge field. Okay. So that's the second gauge field. That's the second gauge field that we know from geometry. One is the Kaluza-Klein gauge field, which is G25 nu, roughly. And the second gauge field is B25 nu. Okay? So 6 has become 2. The 2 we always knew, we loved, we've encountered before, we're happy. 6 was the funny thing. Now I want to understand this 6 becoming 2. So at the special point, I have this unbroken gauge symmetry. Now, what do I have in my hands? I've got this matter field. Okay? I've got this matter field which I'm only going to study directions of this matter field of the form that actually exists. Because that is this pattern. Right? Of the form M3, alpha M3. When alpha is 0, I'm at the gauge unbroken point. And this is what we have. When alpha is non-zero, how much of the gauge invariance should survive? 2 massless gauge fields. Why? Because the part of gauge invariance that survives are the part of those generators that commute with the operator that has a pair.
So it will be U1 plus 1.
It's the rotations, left rotations in the 3 directions, then right rotations in the 3 directions. These are the only ones that survive. Okay? So now, which means how many are broken? So 2 plus 2, so 4 gauge invariances are broken. So now, you see, let's understand what these 4. What were the 4? Suppose this had been just a global symmetry. one in a manifold of solutions that broke the global symmetry. What would the manifold be?
S3.
Mod U1 by U1 would be generated by those by symmetry operations. Modulo those that leave the web invariant. These are the left generators, the things that leave the web invariant. On the left. Right generators, those that leave the web invariant. Okay? So, yeah, along this branch of solutions, there's this 9-parameter set of scalar directions. 4 of these 9 parameters are symmetry related to the original configuration. For each point here, there is a 4-dimensional manifold that was symmetry related to M33. Had the theory not been gauged, this would have given you 4 Goldstone bosons. Okay? But the theory is gauged. How does symmetry breaking work in gauge theories? Every direction that would have become a Goldstone boson is actually eaten up. The degree of freedom is not there because it's gauged. Okay? But where does the degree of freedom go? Degrees of freedom never vanish. It goes into making gauge boson massive. Gauge bosons massive. Okay? That 4 is the difference between 6 and 2. It's the Higgs mechanism. Is this clear?
Yeah.
Okay? Yeah. Right. Okay. Any other questions or comments? Okay? Yeah. Okay, so let's move on. Let's move on. By the way, let me just make one more comment. For the massive gauge bosons, the ones that are Higgs, you could wonder what were the vertex operators. Okay? And if you thought about this, you might be confused about the following point. You might think, well, this guy is going to have the J pluses will have the number changed. Okay? And so this may get a different dimension. But how will it match? So we'd have to make it up with an e to the power ikx. But e to the power ikx gives additional dimension to this as well as this. So how's it working? I'm posing an entirely false paradox, just because I'm getting worried that you guys are not engaging. So please help me resolve my false paradox. What I said is entirely stupid. If I thought the problem through carefully, I would never have said what I said. I just want one of you to explain that. Do you understand my false paradox?
Can you say
It's maybe so stupid that you can't even understand. Okay. The sharp question is, can you tell me what the vertex operator, a little away from the self-view point, can you tell me what the vertex operator for the massive W boson? I told you from field theory, we know that the 4 gauge bosons have to become massive. Okay? The answer is obvious. But I pose such a bad paradox that I just tell you the answer.
But why will they change?
Why will they change? See, so tell me what it would be. If it were, what is the claim that would continue to be the same? Suppose I just had e to the power I square root 2xl by alpha prime xl by x. Suppose this is not allowed. This is not a vertex operator because it's not consistent with the periodicities of x.
Yes, so the rule always is to make 1, 1. So now that you've gone away from the self-dual point, this thing does not continue to have the first factor does not continue to have 1 as the conformal dimension.
So now what does the first factor become? So there are two different issues. A, what is the spectrum of allowed operators in your virtual theory? B, which of them are 1? Now, not being 1, 1 is not so serious because you can fix that up with an e to the pi k.
Yeah, that's true.
But not being there at all is very serious because that can't be fixed. But of course, there's some vertex operator that's near to this because of very much. What? Yes, and what is that vertex operator? You're not answering the question. I'm at self-dual radius. Yeah, this class is turning into a bit of a quiz competition, but it's okay because I'm not seeing you guys. You guys need to read what we do between classes and need to think about it a bit because it doesn't work. It's not physics is not a spectator sport. So the question is, I've written down the vertex operator for the massless gauge bosons, okay, and the self-dual radius. If I move a little bit away from the self-dual radius, if my interpretation of this being Higgs is correct, there must be a vertex operator that's a little bit different from the vertex operator of the massless gauge boson. Because a very low mass Higgs W boson is not very different from a massless. I mean, it is in some ways, but in many ways it's not very different. So I want to know, there's nothing to the question really, but I just want to know what the vertex operator would be. Could somebody write it down?
The mass would be proportional to the width that we give.
Correct. So it will be proportional to the change in the radius. That's absolutely correct.
Oh, e raised to I k xl del x del bar xi because
Where?
Just give it a momenta in the xl direction.
X25 you mean?
Yeah, x25.
Okay.
Wouldn't that work?
I'm not sure I completely understand what you said. Maybe in some. I'll just say the answer now. Yes, certainly. But in the last class, we worked out the spectrum of vertex operators for circle compactification at every radius. This vertex operator was labeled by an N and a W. Do you remember? These were the vertex operators. These guys were the vertex operators with N is equal to W equals 1 and N is equal to W equals minus 1. Vertex operators with N equals W equals 1 and N equals W equals minus 1 existed every day of compactification is. Just that vertex operator, that N and W and that radius. What is the difference? What was special about this radius from that vertex operator point of view? If you remember, when N was equal to W, the operator was purely holomorphic. Sorry, when N was equal to W at the self-dual radius, the operator was purely holomorphic. Move a little bit away from the self-dual radius will not be purely holomorphic. So it will be an operator that will continue to have an e to the power something xl, but will also get an e to the power something xr. Now, this will not have, in general, it will not turn out to be 1, 1. How do we make it 1?
E raised to I k x.
What? E to the power?
I k x.
Yeah. E to the power ikx times this guy.
That's true.
Now, this is sounding strange because this guy goes away from dimension 1 by some amount. This guy goes away from dimension 0 by some amount. But e to the power I
It's
x,
same, right? To make that x, right? Both these brackets, right?
these are not x.
No,
these are-
xl plus xr.
It's not xl plus xr. But it's when you get only xl and no xr. This is a coefficient near 1.
No, when we are moving, I mean, those coefficients are not equal, right? This is, as you said, this is different from 0. I mean, this xr
Yes,
coefficient.
it's 1 plus zeta,
Yeah.
and this is some zeta.
So we need to make both same that to club them, right? Or I'm not understanding.
No. We got that rule not by adding some e to the power x25. We got it from the rule that we wrote down last class. If you open your notes, you'll find the vertex operators and m equals 1, w equals 1 at every radius.
Yeah.
And that's what we do. We just keep n and w equals 1 and change the radius. Okay? It's true that this and this are not independent. There's something, but they're not. It's not that we're adding just this plus this. Okay. Now you might wonder, how am I going to make this 1 Because when I add e to the power ikxi, that adds k squared by alpha prime k squared by 4 to both left and right. So maybe I can make the left part 1, but then wouldn't it be a miracle if the right part also became 1?
Yeah.
It would be a miracle, but we know that that miracle happens. Why?
Oh, because
Because there is a particular binding sector where the mass shell condition will.
Because the level matching condition we worked out switched to NL minus NR is equal to NW. Okay, we've checked that with this rule of quantization of momenta, this is how it works. So that the number of left moving oscillators minus the number of right moving oscillators, that would be in this case 1 and 0, is 1 to make everything work. So it will automatically work out. Okay? So this incredible miracle that you might have thought was entirely unlikely, we've already checked, it happens. Do you remember?
Yes.
Okay? Remember what the point was. We had L0 had to be L0 bar. That was the statement that the left moving and right moving dimension. Then we broke up the L0 into PL squared plus oscillator part.
yeah.
Okay, now PR squared plus oscillator part. Then we looked at what PL squared minus PR squared was. And we got that was an integer. Incredibly enough. You remember it was the same miracle that happened for consistency of the OP. Okay, is this clear, everyone?
Yes.
Okay, great. Okay, now let's move on. Great. Okay, now the various things I want to discuss today, we've got a bit derailed, but doesn't matter. Various things I wanted to discuss today. One of which was the generalization to compactification of not just one but many directions itself. Okay? Nothing new happens beyond 2. So we'll consider 2. Okay? But something new, something different does happen when you compact by 2 directions as opposed to compacted by 1 direction. Okay? Maybe it's easiest to say. Okay, perhaps I'll just do general number. So suppose it's just. Okay, suppose the number we have xa goes to xa plus 2 pi ra. A is equal to 1 to number of compactified directions. And then we have xi, which belong to R 25 minus C1. These are the non-compact directions. Okay, that's the general setup. Just to be okay, yeah, that's the general setup, and let's work with it in what follows. Okay. Now, all we're interested in, the feature that we saw in great detail when we looked at one circuit compactification, namely that the oscillators are unchanged. Every different thing, everything that's fun happens with the zero modes, continues to generalize to this thing for the obvious reasons, the same reasons. Okay? So, we will once again look at winding sectors. XA goes to X is equal to WA 2 pi sigma R. No, 2 pi sigma R. Okay? WA is an integer, so winding number. Okay. How many times the string winds around the 8th circle? Okay. So suppose we're in such a winding number set. Okay. Now, what was the string action? The string action was del alpha x. I'm only interested in the x's. Del alpha x. 1 by 4 pi. That's good. But, you know, we had these various different circles, compactification radii. With these various different compactification radii, which, as we just discussed, could be exchanged for keeping the compactification radii all fixed, but allowing for okay, but allowing for suppose A ran over just one variable. Okay, but allowing for a general constant metric XA, GA, so what Yogesh said, G25. Okay, so I'm going to now switch to that language. When you have many different compactified things, it's more convenient for various purposes. To switch to the language where all the x's are compactified with 2 pi periods. Some standard periodicity. It's like R, periodicity R. Say what dimensions, right? So some fixed dimension R. Okay? But my metric here is 1 by 4 pi alpha prime. Okay? But my metric here is 1 by 4 pi alpha prime G AB
Oh, this is necessarily not flat.
It's not diagonal, it's flat, it's constant.
Oh.
Okay?
Why is it not diagonal? Diagonal with different elements.
Well, we could do this. Who could stop us from doing the offset? Okay? You see, what's going on here is the following. That it's like when we looked at a two-dimensional torus. The simplest tori are rectangular. But that's not the most general kind of circle identification. So, one thing is to have two different circles. But another, more complicated thing, is to have a toroidal compactification of space-time. special tori are products of two circles. One direction, one orthogonal direction, another orthogonal direction. But all tori are out of that form. Because of the twist, right? Or because, in another way of saying it, we can have identification by a lattice that is not rectangular. This we got very used to when we are studying two-dimensional tori. Because this is generalized to every dimension. Okay? So either we consider, what I first wrote down was the simplest, stupidest rectangular kind of toroidal line. It's a product of circles. But in general, it's clear we can do more general things. We can identify by a d-dimensional lattice. That lattice need not be regular. Is this clear? Okay? So there are two things we could do that is equivalent. One, keep the metric what it is, like this, but make the identification XA goes to XA plus EA. Okay? Where this is a particular vector, and the number of such vectors run over the number of compactification directions. M runs from 1 to 7. Do you understand this? We make a C-dimensional lattice in space-time and identify XC by this lattice. Just like we made a two-dimensional lattice when studying the worksheet and identified points on the worksheet, if they differed, by translations by an integer multiple of this, of some lattice. Is this clear? Okay? This is one way of saying it. The second completely equivalent way of saying it is, I will do the coordinate transform so that this identification becomes just x goes to x plus 2 pi r for all x. But of course that coordinate transform, which will continue to keep the metric constant, will not make it keep it diagonal. So I'll give you some arbitrary GAB. Okay? These are entirely equivalent ways of thinking. Okay, but for a point that I want to make now, this will prove to be the more convenient. Okay? I go from one to the other by a field, a linear field. Is this clear? Okay? As we continue our study of the subject, both points of view will prove useful for different things. So we have to get used to thinking in both ways. Is this clear? Okay, excellent. So, now that we've done this, you can look at this Lagrangian and say, okay, great. It's clear from the point of view of Lagrangian that this theory will continue to be solvable and presumably also conformal, essentially because it's a quadratic theory. And this is a constant, doesn't matter what the constant is. You're going to get very similar physics to the other action for any constant GAP. But this point of view also suggests an actual generalization of this. Anyone suggest to me what the generalization might be? Very good. Say
It's a metric function.
to function. That now makes us non-quadratic. That is very different. That generates Einstein's equations. As who told us this? Pranjal explained to us. When you do that, you can do that, but that's a very complicated story. The only continues to be conformably invariant if the metric obeys Einstein's equation.
What is the question again?
Question is, I've got this nice set of solvable fields, conformal field theories, but there's a generalization of this. I've not looked of the obvious conformal field theories. I've not exhausted them. Okay? The answer is that you can also have the field epsilon of theta. where BAB is another constant. B is necessarily antisymmetric because epsilon is antisymmetric. So otherwise it vanishes. Okay? What is it? It's the B mu nu field. Just like this was the value of the metric on which our strings are propagated. This is the background value of BAB on which strings are propagated. Why did we not encounter this in the case of one circle identification? Because BAB is antisymmetric, so there is only one component, there's nothing to do there. So you've got two components, you've got room to play. Now, when we studied it in the last semester, when we studied this B field, we studied its gauge independence. And in particular, we talked about H, which was dB, as being the field strength which captured the gauge invariant quantity. B was invariant under the gauge symmetry, which was B goes to B plus dA. A is any one form. The generalization of the gauge invariance of Maxwell. Okay? And so, if you might want to say, well, this looks suspiciously like doing nothing. Because if B is constant, then H, which is dB, is 0. And therefore there is no field strength associated. You might want to say that. But you must be careful because you might say the same about constant gauge potentials. But we know that in the presence of a circle, a constant gauge potential is not gauge, pure gauge. Because there's a gauge invariant operator, namely the Wilson line. Okay? That is not pure gauge, even though the field strength vanishes. And here it's the same thing, because in space-time, you've got a torus. The integral of B over that torus is gauge invariant for the same reason. Why is it gauge invariant? Because integral B is equal to integral B plus dA. Because this vanishes by Gauss's. That's Stokes theorem, whatever. The theorem that total derivative integrated vanishes, so we're going to call that. Okay? So this is, so when we got, and you see again from this point of view, you need at least two directions to be compactified for this. You need a torus. But you've got plenty of different tori. So these B's now are not gauge artifacts anymore.
What is B doing? G is like scaling.
B is doing something new. We'll soon see what it's doing. It's not. It's like the question, if you had a Wilson line in a gauge theory, what is it doing? What it does is change the quantization of charged particles. Quantization is conditional charged particles.
No, I'm saying you explained this because changing the direction in which you are compactifying the DAB. But
so this is different. I'm sorry. Yeah, this is different. It's not part of it. It's not part of the geometrical compact. It's more data than geometrical compact.
Some flux to the compact.
It's Wilson lines. It's the Wilson surfaces of B. Okay? It's like asking, yeah. We'll see. Hang on. Wait. I'm going to have to go in 10-15 minutes, but after, hopefully we get to that. Is this clear? Okay. Now, what I'm going to do is to try to, okay, now what I'm going to do is to try to see how all of this affects the quantization of the string. So now I've set myself a new problem. The problem is to try to understand the quantization of this. Okay? Great. Okay. Now the first thing to notice is that this term, okay, is a part the first thing to notice is that this term does not change the equations of motion, the classical equations of motion of our 2D quantum field theory. Why not? The easy way to say why not is to know that we can write that equivalently as del alpha of BAB alpha epsilon alpha beta XA del beta XB minus 0. Why minus 0?
Because BAB epsilon beta are constant.
Because BAB is a constant, and because by del alpha,
Oh, that's equations of motion.
no, that's 0 because of
Oh,
anticipation.
sorry.
Okay, so this term is exactly equal to this term. Okay, so it is locally, it's a total derivative. Now, because x is not simply valued, the total derivative doesn't necessarily integrate to 0. But because it's a total derivative, any local variation, any infinitesimal variation of this action will vanish. Okay, it's like adding f/f to the QC derivative. It's a total derivative. Doesn't necessarily integrate to 0, but certainly doesn't affect the equations of motion. Okay, and we will check that explicitly. Basically, what you'll find is that the term coming from varying this cancels against the term coming from varying this. Okay? So the equations of motion of our theory are the same. So we continue to have oscillators and zero modes and blah blah blah. Okay? Now what we want to do is to see whether this term affects the quantization. Okay? We want to see whether this term affects the quantization of whether this term affects the quantization of the solutions. Okay? So how do we do the quantization? We take these solutions, evaluate the symplectic form on the space of these solutions. So, okay, we did all that last semester. Suppose we take something that is oscillator times oscillator. A solution that is oscillator times oscillator. So we've got the whole solution can be written as 0 mode plus oscillators. So if we take oscillator times oscillator, those oscillator fluctuations are single valued. So this total derivative term does integrate to 0. So for oscillator times oscillator, this total derivative is not just classically, it's also quantum mechanically irrelevant. Okay? What about oscillator times 0 mode? Well, this expression, okay, being a total derivative integrates to 0. Because an oscillator has some momentum, it integrates against the 0 mode that has no momentum. Anything that has a momentum, periodic of the cell, integrates to 0. The only place that this term can affect is 0 mode times 0. Okay? Similarly for this thing. You see, by field redefinition, we can, by this Y field redefinition, we can completely diagonalize this term. The only thing that's affected are the identifications of the x's. Once again, for oscillators, it doesn't matter. Once again, for oscillator times 0 mode, it's 0. It's only for 0 mode times 0 mode that matters. So, we see a great thing. That this Lagrangian looked quite complicated, but we just argued that the oscillator part is unaffected. Okay, it doesn't matter what the GAB is. It doesn't matter what the B is. Roughly speaking, it's because the oscillations are happening locally. And locally, this is not changing the physics. All the changes from global scale. Okay, is this clear? Okay, so the only changes are in the 0 mode sector. So in order to understand that change, let's just try to understand the 0 mode sequence. So we just plug in 0 mode into the action and quantize the 0 mode action. Forget about the oscillators, which will be unchanged. Is this clear? Okay. So let's do that. So we know that the equations of motion tell us that x and x bar, so we know that the solution to the equations of motion are xa is equal to WA sigma. Maybe R, we keep an R. Remember, boundary conditions, all of them have been identification R. All the funny stuff is going to the GA. Okay. Plus square root alpha prime PA tau. Did I get the square root alpha prime right? I think so. Okay, so this is our 0 mode thing. But in fact, what I'm going to do is I'll just write this as plus xa of tau. I'll put this into Lagrangian, quantize that Lagrangian. That Lagrangian will tell me that it's linear in time. The solution will tell me this. I'll just put it into the Lagrangian. Okay. Remember, this coefficient could be a function of tau because it was an integer. So there's no dynamics there. So that I can just set once. But there's dynamics in xa, and I will try to understand the quantity. Now you just take that and plug that into this Lagrangian. So what do I get? I get 1 by 2 alpha prime GAB xa dot xb dot. Now in the usual conventions do they put 1 by 2 by alpha prime outside BAB as well? Let me check that. Yeah, puts it, so we follow it. So, plus, he has 1 by alpha prime BM in it. Maybe he puts it 2 pi. He puts it 2 pi. I think this is how he affects it. No, sorry. 2 pi. Sorry. 2 pi goes away for the same reason. Sorry, this is how it is. Yeah. Okay. So now you see we got rid of the 2 pi by doing the sigma integral. Okay. Plus BAB. Okay. Plus, of course, this part. We also got contribution from winding times winding. Okay. So that is GAB. Now, there we get, okay, so this part was from x dot times x dot. Because here if we had one time derivative, we also have the second derivative to be times, that's x dot times x dot or winding times winding. Okay? Now, what about the guy that was winding times winding? That guy gives WAR. Exactly. WAR. Once again, we get an integral of 2 pi from the sigma integral. Okay, so we will get WA, WB, R square. Okay, and now let's look at the BAB. BAB has this epsilon. So it has one tau integral, the other one is a sigma integral. Okay? Therefore, what we are going to get is plus two BAB WA to XB dot. Okay, and whether it's plus 2 or minus 2 depends on whether our convention, what our convention of epsilon was. Yes, I'll choose the convention for it to be plus epsilon. Okay, so what we have here is S is equal to 1 by 2 alpha prime. Okay, so this is just some constant, so let's list what that is. GAB WA WB R squared. Okay, and then this the terms that involve X dot. GAB XA dot XB dot by 2 alpha prime plus BAB WA XB dot by
This is an R there.
R.
EAB.
Thank you. Okay. Now let me do the canonical quantization. What is the momentum conjugate to XA? BA is the derivative of the resultant with respect to XA. GAB XB dot by alpha prime. This is the analog of what we got with one thing. Now there's a new term. BA
times
plus B or minus 2N. May change signs of this as well. BAB WB R by alpha. Yes.
So here you have XB dot.
XA dot, XB dot,
Here, that's the case type.
which, yeah,
Yeah.
it's a dummy basic.
Yeah, it's
Is this correct?
I didn't notice the number.
First, it also includes in tau.
Tau is what?
Exactly. How do you get this?
This is Lagrange. We do canonical quantization.
We wrote that.
The first time is just a constant, it's not an
In the first term. Yeah, okay, I'm sorry. Lagrange. Okay, and I may have got potential energy, that's the energy. Okay, I've got intention. That's action. Okay. Yeah. Why is that minus? Because when Minkowski space. So when she del alpha is dt x dot squared minus x prime squared. My thought should be x prime squared minus x dot squared. Okay, then I need a minus sign. Okay. You understand, right? It's the usual reason. It's phi dot squared minus phi prime squared is the action. Okay, this is the key point. The key point is that the conjugate momentum has got shifted by this new non-perturbative term. Even though it didn't affect the equation of mass. Now, let me complete this quantization.
We need to put commutator.
Exactly. We need to put commutator. So we have XA PB is equal to I. Exactly. But now, look at this. So what is quantized? The fact that XA goes to XA plus R gives you quantization of PA. PA has to be equal to M by R. Why? Because wave functions are e to the power I P dot x. So x goes to x plus R requires this quantization on P. It's quantization on P, not on GAB x dot by alpha, but on P, including this beta. Is this clear? Okay? So let's continue here. So now what we do is to get to solve for x dot. Because PAs are some definite quantized numbers. So we have the equation M by R is equal to GAB x P dot by alpha prime. And M is what I call N last time. So N. Okay? Which implies that xp dot GAB xp dot xp dot is equal to GAB times, and this should be NE. So NB, there's an alpha prime. I lost that. Yeah, that's probably okay. NB alpha prime by R plus GAB B GAC BCB. What am I doing? This is X A dot X A B C W C R. Is this clear? Okay? And therefore, the expansion is X is equal to WA sigma R plus this stuff. Okay? Plus GAB alpha prime NB by R mine plus GABBB CWC R times that. We finish it. Will it last 5 minutes?
4 minutes.
4 minutes. Is this clear? Now let's see how this reduces to what we had before. For simplicity, let's just set this G's to be 1 and B's to be 0. In which case we had X, which was winding, plus N by R times tau, which was alpha prime times times P, and P with N by R. So this is some generalization of what we had before. Oh, and where is, yeah. But the important thing is here that this thing has an effective shift in the moment. Okay? So now we need to rewrite this in terms of P left and P right. Okay? So what was our P left and P right? Well, what we do is to write tau is equal to x plus x minus, maybe by 2. We'll get the 2's right by comparing with standard form. Okay, sigma is equal to x plus minus x minus. Plug in and look at the coefficients of x plus and x minus. Let's say the coefficient of x plus are p left and p right. Let's get the coefficient of p plus. So xa is equal to pa plus x plus pa minus x minus. Okay? And p plus a is equal to, clearly from this way of looking at it, w a r plus GAB alpha prime NB by R plus GAB BBC WC R, and P minus A is equal to minus WAR plus GAB alpha prime NB by R plus GAB BBC WC R. Okay. Now, suppose we want to deal with P's. Suppose our definition of PL is that when we have e to the power ikx, then PL is equal to PR is equal to K. Okay? So that should be when we set W to 0, we get just alpha prime. So this is correct. Okay? So this is a definition of P in which e to the power, the vertex operator e to the power I PLX will be by PR XL XR scaling dimensions alpha prime PL squared by 4 alpha prime PR squared by 4. Okay? With this definition of PL. Okay, these are the correct formulas for PL. PL and PR.